All right, so welcome everyone to February 7th meeting. Okay, so RASC Halifax Centre respectfully acknowledges that we live and observe on the unceded territory of the McGrath people. And the RASC believes in and practices inclusivity and diversity. RASC Halifax Centre welcomes all with an interest in astronomy. So, today, we're going to move into a photo montage, followed by our special presentation by Devin Williams. And then we'll have a brief social break, followed by Food for the Soul with Paul Heath. I'll mention some outreach opportunities, and Tony McGrath and Judy Black will give update from the board. And we'll end with what's up in the February sky.
Clouds.
Clouds, yes. So, photo montage. And yeah, we haven't got a lot of photos because of clouds. But we have some.
We have photos of clouds.
Yes, we do. Actually, that's true. And Mike Beauchat's got a photo of a cloud. All right. Got it. Perfect. Okay, so this is a picture of the full moon from January 3rd, taken by Judy Black. With his C-Star S30. And you're going to find that a lot of the images today are taken with an S30 or an S50 or a Dwarf 2 because of the lousy January weather. People were able to take advantage of a short period of cloudless skies and use their smart telescopes. Okay, another photo from Jerry, sunspots on January 20th. And there's a nice big group in the middle. And the North America Nebula, NGC 7000 from Jerry Black with his S30. And I believe that Jerry's been taking the raw data from his S30 and putting it through PixInsight, right? And it does a nice job. And the Rosette Nebula, again from Jerry, with his S30.
So Jerry is obviously making good use of his new toy, but can you blame the weather on him then?
I don't know. You got the toy a couple months ago. Michael Beauchat snapped this shot of the moon out of his bedroom, or out of his apartment window. Moon's a little bit overexposed, but Jupiter shows up quite nicely as a result of that. And I don't know if this is showing up from the back of the room, but Michael got some of the northern lights on the evening, early evening, I think around 6:30-ish of January 20th. And you can just see some of the pillars and a bit of the color, which is not bad from downtown Halifax with all the light glow. If you go to darker skies, you end up with something like this. This is what Barry Burgess got the same night. Lovely shot, lots of colors, and not to disappoint Blair, there's a few clouds in the distance. Barry Burgess, the full winter moon rising on January 3rd. Barry always takes great shots of the moon in landscape mode. Paul Gray's been busy reprocessing some older data and has got some really great pictures up on the Facebook page. Showing lots of dust cloud nebulosity. This is the Cocoon Nebula. And the Pac-Man Nebula. Love this one. This is the Embryo Nebula, NGC 1333. This a tough target. I've tried to image this from the city and it's impossible, but Paul, having the advantage of Annapolis Valley, reasonably dark skies, really outdid himself, I think, with this one. And the Running Man Nebula, NGC 1977. This is just above the Orion Nebula. It doesn't often get sole billing, but it certainly deserves it in this shot. This is an image I took of the sunspots on January 20th with the Dwarf 2. And the waxing gibbous moon on the 23rd, again with the Dwarf 2. Crab Nebula, Messier 1. Image from Clayton Park. Beehive Cluster, Messier 44. Unfortunately, the few nights we've had clear skies in January, there was also a lot of full moon or nearly full moon. So imaging anything other than star clusters was pretty much impossible. And Messier 48 in Hydra. And Messier 67, the Golden Eye Cluster, captured with my Dwarf 2. And then we've got, to finish off, a couple images from Norman Schneiderman. Sunspots, January 17th, imaged with his C-Star S50. And the Orion Nebula, M42, from Norman, again, imaged with an S50. So not as many shots as we normally have, but you know, this particular shot from Norman, that's 4 minutes of aggregated integration time. So all you need is a little break in the clouds with these smart telescopes, and you can gather some photons. And I think that's it for the photo montage. So I think we'll move on then to our guest speaker, Devin, and Judy Black is going to introduce Devin.
Hi there. I'm really pleased to announce our guest speaker for this month. We approached him a few months back, in fact, probably latter part of last year, to see whether or not he would be available at this time, and yay, he is. Devin Williams is a PhD candidate here at SMU. He's a maritimer, born New Brunswick, moved to Nova Scotia to attend this wonderful university, and he's been working on his, through his master's and his PhD theses, he's been working on this particular topic that he is going to address with us today regarding galaxy mergers. So without further ado, I will hand it over.
Okay, I'll stand over here out of the way. Hi everyone. As Judy said, my name is Devin. I'm in the PhD program here at SMU. So I just want to say thanks very much for giving me the opportunity to talk to you about my research today. So my talk today is going to be on building galaxy outskirts, the role of galaxy mergers, and cosmic environment. And throughout my talk, I'm going to try and keep the technical details and some of the boring science plots to a minimum, just in case everyone in the room isn't an expert. But if anybody wants the gory details afterwards, please feel free to ask me. I've got a whole bunch of additional slides with all those nice technical plots if anyone's interested. So first I just want to start with a brief introduction to galaxies, their different properties, how we study them, just so everyone's kind of on the same page, give a little background context for my work. So galaxies are these vast gravitationally bound systems. They contain anywhere from hundreds of millions to trillions of stars. They can be hundreds of thousands of light years across. They have large reservoirs of interstellar gas like hydrogen. They have these microscopic dust grains made of silicates and carbon compounds. They have black holes, anywhere from small ones a few times the size of our sun to supermassive black holes at their center, and surrounded by this mysterious dark matter that we don't know too much about and that I won't talk a lot about in my talk today because it's well beyond my field of study. So how do we know that galaxies are made up of all of these different things? How do we study a galaxy's internal structure and composition? We look at it in different wavelengths of light. So just a quick refresher from high school, in case we're not all up to speed. Remember, we shine a white light through a prism, breaks it into its different colors or its wavelengths of light. Our eyes pick up this visible range, that's the rainbows that we see. But we know that there's other wavelengths of light that are used for all sorts of purposes, right? We have the short wavelength X-rays we use in hospitals, long wavelength radio waves we use for telecommunication. So the same thing happens with studying galaxies. We look at them in different wavelengths of light by using either different telescopes or different filters that block out certain bands. And this allows us to get at the composition or the different components of galaxies. So on my large image here, you see some smaller cutouts on the side. So that's just showing different parts of the Centaurus A galaxy here and how different components light up in different wavelengths. And this is because different gases give off different wavelengths of light, and we can test this in labs on Earth. So that's how we know what's going on, what's inside there. So these are some examples from the James Webb Space Telescope, just showing how different images in different wavelengths, so that's the color panels you see, highlight different regions of the galaxy and also different compositions, so molecular hydrogen or iron ions. So that's kind of how we get at what galaxies are made of. So what have we learned about galaxies in the years of studying them? Well, we've learned they come in different shapes and internal structural components, what we refer to as their morphologies in astronomy. So some galaxies can be spiral and blue. They have these, disc shape. When you see them edge on, they're very flat. So those are like NGC 1300 here or Milky Way. Other galaxies really lack all of these spiral structure, these disk components, and are much redder and rounder like M49 here. So in astronomy, we group these galaxies into two broad categories we call elliptical and spiral, based on these morphologies, these shapes. And we have this system thanks to Edwin Hubble of the Hubble Space Telescope. So his work in the early 1900s, he observed a bunch of galaxies, came up with these two classes, and then he further classified them based on different shapes and features. So how round or oval an elliptical galaxy is, or how tight the spiral arms of a spiral are. And then as galaxy evolution researchers, we're trying to probe what are the processes that are changing galaxies' morphologies as they evolve along this sequence. And so, as we've already seen with these two examples here, galaxies also come in different colors. And these colors tell us about the types of stars that are dominating a galaxy's population, and also its level of star formation activity. So to explain these 2 points, in case everyone's not aware, there are different types of stars. They have different properties. Specifically, the most massive stars are going to burn the hottest and brightest, and they're bluer in color. We call these O and B class stars. Now, the cooler, lower mass stars that are much dimmer in comparison are more redder or orange in color. And the key thing to take away here is that the galaxy's light that we're getting is really just the sum of all these billions of stars. So the global color of the galaxy will tell us what types of stars are kind of dominating certain regions in the galaxy. And the other really key thing to keep in mind is that these stars have different lifetimes based on how fast they burn through their fuel. So these stars are just balls of gas that are lit on fire. The most massive stars are going to burn through their material much, much faster, so they only last very short time scales, at least in astronomical terms, so about 1 to 10 million years. On the other hand, the lower mass, cooler stars, like these red ones, they last anywhere from 10 to 100 billion years, so much, much, much longer. So what this tells us about star formation in a galaxy is when we look at a galaxy in different wavelengths, we can get a feel of its true color. If it's much, much more bluer in color, this is telling us that it's recently formed some stars, and that's why we see a lot of these hot, blue, short-lived massive stars still around, right? So a cloud of gas condensed under gravity, compresses so tightly it ignites, it creates a bunch of stars. But if the galaxy is redder in color, then there hasn't been any new star formation for billions of years. The only stars that are left over are those long-lived lower mass stars. And so we say the galaxy is no longer star forming, or we call it a quiescent galaxy. So throughout my talk today, when we get to the results, I study both of these types of galaxies. So you're going to see these two acronyms pop up time and time again on some slides, red QG, blue SFG. Just to orient yourselves, it's the two types of galaxies, the non-star forming and the star forming ones. Another thing I want to introduce about galaxies is maybe something not everybody is familiar with, and that's galaxies are not randomly distributed throughout space. They actually reside in these different components of this vast interconnected system called the cosmic web. So if you could actually take a chunk of space, zoom out and look at it, it would look like this little cube here. And what I've done is blown up a region of this cube so we can kind of see what's going on. And so the yellow that you see are basically all the stars and gas. I should say this is a simulated photo. We can't actually take a photo of this, detail of the cosmic web. And then the structure of the cosmic web that you see in blue is actually made of dark matter. And so there are different environments that I want to highlight throughout this cosmic web, because this is really where research right now is trying to understand how are galaxies affected in these different environments. So you'll notice that there's these regions where a lot of galaxies and stars pool together. So we call these the nodes of the cosmic web, or more simply or more commonly known as galaxy clusters. This is where we find a whole bunch of galaxies clustered together. Now these clusters are all connected to one another by these long, thin, branch-like regions we call cosmic filaments. That's what highlighted in green here. And then in between these two features where we find very little gas in galaxies are these areas we call cosmic voids. So I'm really interested in these cluster regions, and part of my talk today is going to be about these, because this is where we're finding a lot of galaxies, but we don't really have a good understanding of how they're affected over large timescales in these regions. So a little bit about galaxy clusters. This is an image from the James Webb Space Telescope of one of the MAX clusters. I'm not going to read the whole long number name at the top, but you can see it there. And so these are some of the largest gravitationally bound structures anywhere in the universe. They can span millions of light years across. They contain hundreds to thousands of galaxies, and they have a lot of dense, hot, turbulent gas, intergalactic gas, we call the intracluster medium, or ICM. This is another example of a cluster on the sky, actually a much closer cluster. This is the Virgo cluster, and we're actually neighbors with it in a much larger supercluster of galaxies. So the little white labels you see scattered throughout the image are just different galaxies that are in this cluster. And so I don't want you to think it's just a projection thing. They really are inhabiting the same region of space. And so in this video, it's going to quickly, hopefully it plays, yes, just going to quickly show you a simulation of what we think life might be like inside one of these clusters. So all the little white points you see are just different galaxies that are falling into these clusters, orbiting around them, and the big kind of white clouds that you're seeing, that's that hot, turbulent ICM gas that I was talking about. But these are really just predictions from simulations, and it's really just kind of an n-body model, so it's just how things move under gravity. We don't really understand how this is affecting galaxy properties, composition, interactions between them, all sorts of things like that. So that's kind of what my work is trying to get at. So that brings me to the next part of my talk, where I'm going to go over how we study galaxy evolution, and then introduce the specific questions that my research is trying to answer. So first, for some basics, how do we actually study galaxies changing over billions of years? I only have 4 years for the PhD, so I don't have a billion years to wait around and watch one of them grow. So what we do is we take advantage of the fact that in our universe, things further away, we're also looking at them how they existed further back in time, right? Something a million light years ago, you're looking at light as it existed a million years ago. So by taking images of galaxies at a whole bunch of different distances or times, we can kind of piece them all together and form this larger evolutionary picture, almost like snapshots to form a movie reel, if you think of it that way. Now, the other thing to keep in mind is that these galaxies are so far away that during the time that the light is traveling to us, the universe is expanding. And so the space between us is stretching, and this stretches the light wave that we get. And so we say the galaxy's been redshifted. So this is very similar to the Doppler effect that we experience here every day on Earth. If you've ever been standing on the street, you notice an ambulance come towards you and the siren sounds a little different as it approaches you and when it recedes you. So that's just the sound wave, either extending or compressing. Same thing's happening with the galaxy light. And so we're able to measure this redshift, this amount of stretching, and this gives us a rough estimate about how far away the galaxy is when we stop talking about distances in light years or even parsecs and we start to just use redshift values. You're going to hear me talk about redshift ranges a lot throughout my talk. It basically just means period of cosmic history. Redshift is times. So specifically in my work, what I'm interested in is the processes that drive galaxy mass assembly. Or more simply put, how are galaxies acquiring new stars over time? What's making them grow larger? So you might think, well, it's just simply star formation. We talked about that already. Gas collapses, forms stars. That's how galaxies grow. It turns out star formation can't be the only way that they grow, because we ran into two problems. One is that we found some star-forming galaxies, those big blue spirals, that are so massive that even if you assumed perfectly efficient star formation since the Big Bang till now, and assumed a very high rate of star formation, you could not have formed enough stars to make them as big as they are. So that was problem one. And problem two is that in samples of the quiescent galaxies, right, those red ones that are not forming stars, we've seen signs of growth over large timescales. We're comparing time bins between these samples. So something else is clearly driving this growth. So I like these two plots. This really highlights the discrepancy really nicely. The top one is just showing the average rate of star formation in galaxies as a function of time. Big Bang on the right, today on the left. You can see it peaked about 10 billion years ago, and then since then it's been starting to fall. Now this red square I've highlighted is a period of time very close to the period that I study and that I'll talk about in a bit, but it matches with the plot below. And this is a study by Van Dokkum et al., which very simply just showed that during a time of the universe where star formation rates, this blue line, are falling, the net mass growth rate of some of the big galaxies, particularly the big red ones, is much, much higher, but almost an order of magnitude higher than what's possible through star formation. So clearly something else is driving growth of the big, big galaxies. And so this is kind of where it gets into, because what the leading explanation is that galaxies grow through mergers. So they interact with one another, they're able to swap material, or what we could say accrete. They're able to take stars and gas from each other, or you can have a big galaxy that eats up a bunch of smaller galaxies. And we know that this is occurring because we have images of galaxies caught in the middle of the act. So that's what some of these panels are showing here on the left. So we have images of galaxies literally in the process of merging. So we know this happens. Here are some nice larger enlarged examples. This is NGC 4676, and we have two ARP 273 and 107. The problem is that just catching random glimpses of these interactions don't really tell us a lot about how does this merging process contribute to the growth in galaxies over large timescales. Does it matter, does it mean more to certain types of galaxies? Does it matter what environments you're in, right, in that cosmic web? These are all questions that kind of need answering. Now, there are different types of mergers just because we've kind of defined them that way, just based on the size and the types of the galaxies involved. So there's what's called minor merger, just between a large and a small galaxy. During these interactions, the smaller galaxy is going to have its material just slowly stripped away, ripped apart, and it eventually just become part of the larger galaxy. Maybe either get added to the disk, like you see in the top example here, and kind of disappears. Major mergers are between two similar sized galaxies, and these are much more chaotic and violent interactions. Predictions say that if it's two disk galaxies, they're going to come out and look like one big irregular or elliptical galaxy. They're going to lose their disks because it's just such a turbulent interaction. But not much else is known about, what types of merger, which of these mergers are more important. Did it change over the universe's history? Does it matter what type of galaxy? So these are some of the questions that still need answering. So there are predictions from simulations about how much mergers should contribute, but these have not been tested thoroughly at all by observational data, and so theory can really only take us so far. So this plot really highlights that and what's going on. I've made some simplified labels so it's kind of easier to follow. Basically on the y-axis, it's just showing the percent of total galaxy mass that could come from mergers, and on the x-axis, it's showing the size of the galaxy. Big galaxies on the right, small galaxies on the left. Now in the two panels, on the far side panel, on the right side of the slide here, the color curves you see are different simulations, so different predictions. So you can see they all sort of agree that this should contribute more to the higher mass galaxies, but they all differ in exactly the percentages that mergers should be giving. And the more important part is that these gray dots you see here in the left panel, these are just some of the very limited observational tests that we've done of these predictions. And these dots are all representing about one, sometimes at most 3 or 4 galaxies. So very, very small samples, not enough to really test these predictions correctly. And so we really need to address this with a very large sample. And so that's what I do in my work. And I'll talk a bit about my sample in a moment. The other point that is debated right now in the literature is what impact that living in these dense cluster environments has on how galaxies grow and how it regulates mergers between them. Because you might think, just from a simple argument, galaxy clusters have more galaxies, more things to merge with, you're going to have more mergers. But actually, the predictions tell us that galaxies in these regions might be moving so fast relative to one another that they can't actually slow down and merge. So you can almost think of it like two bees in a beehive that are just whizzing by each other. They can't slow down and actually, interact. The other thing is, in these cluster environments, we've seen signs in some galaxies of these elongated tails of material, stars and gas being stripped off the back in one direction. And this is coming from them encountering that hot, turbulent gas. So back in that simulation video, when you're looking at the clusters, that big cloud of gas moving, when galaxies slam into that, it's almost like hitting a big dust storm in the Sahara, and it's going to blow you back. So it can actually remove some of the material. The problem is we don't know much about other than this happens. We don't know how much it contributes. Has it changed over time? Does it only happen to some galaxies? We're not really sure. We just randomly see this from time to time, this stripping. Just as a recap thus far, so what are my objectives? Well, I want to study how galaxies grow in mass. Particularly, I want to better understand how mergers contribute. And I also want to test and investigate what impact you have from living in these dense clusters. So how am I going to do this? I'm going to trace the evolution of galaxy stellar halos. So in case anyone's not familiar, what a stellar halo is really just this term that we use to collectively refer to all the stars and gas and little star clusters or globular clusters that are in the outskirts of galaxies. Now, they're called halos because sometimes they're nice and symmetrical and spherical, like in the Sombrero galaxy or in NGC 474, so that's where that halo term comes from. But other times they're not that symmetrical. And this is why stellar halos are prime areas in galaxies for me to look to probe the impact of environment on galaxies. Because galaxy outskirts can retain observational signatures that indicate past interactions has happened. So for instance, some of these streaks and arcs that you see in these halos here are evidence that something has disturbed that galaxy, some external factor, whether it's been some cloud of gas or another galaxy. And this really comes from predictions from simulations, which is really summarized nicely in this video. So this is basically my entire research project is summarized in this video of what I'm trying to do. So this is a simulation of a galaxy growing through mergers. So it focuses on a galaxy in the middle. Billions of years are going by. As this happens, more and more galaxies, which are the other yellow bits that you see, start to fall inwards, merge with the central galaxy. And then as time elapses, you start to see this extended halo of material start to form, and you can even see some of those streams and arcs that we just looked at in the last two images. So this is where we think those are coming from. It's material that came from mergers that just hasn't quite settled into the perfect spherical halo like something like the Sombrero galaxy has. So really these predictions are what I'm trying to test with large observational samples to understand, is this really occurring and how much is it occurring? Back to the recap. So I want to study mass growth, mergers, and cluster regions. How am I going to do it? I'm going to study the buildup of stellar halos. What do I need to do that? Well, I'm going to need a large galaxy sample spread across a wide range of time so that I can study population trends and thoroughly test those predictions about merger growth. I'm going to need deep multi-wavelength images. So this means images that can get at really, really faint brightness levels, because those faint outskirts of galaxies are very hard to detect. And I'm going to need multi-wavelength images so I can, as we looked earlier, look at them in different wavelengths of light. And then lastly, I'm going to need a method to analyze and quantify these stellar halos that can compare one-to-one with predictions, so I can actually test these predictions. So that brings me to my data sets and methodology that I use for this project, which has been building throughout my master's and my PhD to get to where we are today. So the images that I use in my work are coming from two large area ground-based imaging surveys, the CLOUD survey on the Canada-France-Hawaii telescope and the HSC SSP survey on the Subaru telescope. So both of these telescopes are situated on top of a volcano in Hawaii, Mauna Kea, with several other facilities. So we get really, really great seeing, great observational conditions up there. And in total between the two surveys, there was just under 400 nights of observation, I think, between the two of them combined. So quite a lot of images. The observations were taken on 4 separate fields on the sky. So this just basically means that we've sampled a lot of cosmic environments, so we're not biased because we pointed the telescopes just in one region of space. We really sample a lot of areas. And in total, we cover about 18.5 degrees squared, down to very, very, very low depths, so very, very low brightness levels. So the images that we get look like something like this big 4200 by 4200 pixel image from the telescope. They're taken in 6 different broadband filters, the U-Grizzly filters, which span rest frame wavelength of 3,000 to 10,000 angstroms, which is basically UV to near infrared, in case anyone's not familiar with the angstroms. And then 2 galaxies that I've highlighted here in the boxes on the right are 2 galaxies from my high redshift sample, so my far away sample. And even though they are quite distant and we're looking at ground-based images, and I haven't applied any image corrections, which I'm going to talk about in just a moment, you can still make out some pretty clear spiral features in the bottom one. The top one actually looks like the Sombrero galaxy side on. It's got a bit of a halo. So really, really great detail. So these catalogs give me a very large sample of galaxies to pick from. So I said earlier, remember those predictions have only really been tested with a handful of galaxies? Well, I have 330,000 galaxies, just about over that. And these galaxies spread a wide range of properties. So their stellar masses are down to 10 to the 9.5 solar masses, which may not mean a lot to the non-astronomers in the room. So you can think of it as I study galaxies about 1% of the Milky Way's mass, all the way to 10 times the Milky Way's mass. So a wide range of galaxies. And these galaxies are also situated over a large redshift range, about 0.1 to 1.1, which is about 6 billion years of cosmic history, specifically 1 billion years ago to about 7 billion years ago. That's kind of the time period that I'm looking at. So throughout my talk, you're going to see high mass sample and low mass sample come up quite a bit. I'm going to talk about these two because I've grouped my galaxy sample into these two bins, big galaxies, small galaxies. And to orient yourselves, you can think of low mass galaxies as anything smaller than about half a Milky Way, and the big galaxies are everything larger than that. Now, I also mentioned that I study both the star-forming and the quiescent galaxies, the non-star-forming ones. So how we separate our sample into those two groups, we use what's called a color-color diagram. So without getting too technical, basically how this works is you look at galaxies in two specific colors on the y and x axis, and when you do so, quiescent galaxies and star-forming galaxies form kind of two very distinct groups of points on these plots, which allows you to separate them. But as you can see in this top plot, there's this black dividing line, and there's this kind of area where it gets murky and maybe you can have some contamination between the two. So what our group did was develop this novel approach that uses machine learning to create an optimal dividing line for each individual galaxy, rather than just one line for your whole sample. And it incorporates more than just the colors. It incorporates mass and redshift and some other properties. So that way it's a much more thorough and you get a much more pure quiescent star-forming classification. So in total, in the 330,000 galaxies, we have about 73% are star-forming, the rest are quiescent, pretty typical fractions for this period of the universe. So on the note of my quiescent sample specifically, I'm able to tell whether they're in clusters or not. I can discuss later if anyone's interested about why only quiescent galaxies. It kind of comes down to the methodology and more importantly the data that we had available to us. But in any effect, I developed this code that runs on our HSC cloud sample and detects if a galaxy is in a cluster. How it works, basically in a nutshell, is we take these confirmed cluster locations from the literature. So we know there's a cluster there, multiple studies and different types of data has confirmed they're there. Then we look for galaxies in our sample in a cylinder around these clusters. So just your RA deck on the sky is your X and Y of the cylinder, and then the length of the cylinder is the galaxy's distance or its redshift. And so I said earlier, remember that we know galaxy distances approximately because of this redshift thing. We don't know them right to a finite centimeter. So there's some uncertainty as to where the galaxy is distance-wise. So what I've done to address that issue is in the code, it basically iterates 1,000 times. Each time it adjusts the distance that we've assigned the galaxy based on their errors. So sometimes galaxies with big distance or big redshift errors, they're going to pop in and out of the cylinder. At the end of this, it gives you a cluster membership probability of how many times the galaxy was actually confirmed to be in the cluster. So that way you can get rid of interlopers that aren't really part of the cluster, they're just a projection on the sky, and their distance errors pop them in every now and then. And you can say things like, only look at the sample that were in this cluster 90% of the time, or 95% of the time, stuff like that. So onto the methods of how I'm studying stellar halos. So I mentioned I'm going to need a way to get at the stellar halo material, quantify it, and compare with predictions. So what I do in my work is I extract galaxy light profiles. They're surface brightness profiles. So very simply, these just look at a galaxy's brightness as a function of distance from its center. And as this plot shows, when you look at the outer regions of these profiles, what you're analyzing is this material in galaxy outskirts. And then what you're able to do is by looking at how the slopes or the intensities of these profiles change, will tell you a little bit about what processes are driving the underlying growth in galaxies. So different types of mergers, for instance, or star formation. Now these are just illustrative purposes, so they're exaggerated. But we get different effects to the profiles depending on what's going on. And we have this information from simulations. So this is why I use these light profiles. There's very clear predictions about what should happen to a profile shape given what's going on in the background. So this allows me to kind of ferret that out in real observational data. So how do we get at these light profiles? We extract them using a code that our group developed strictly for this research called GalPrime. So the development was led by a collaborator of ours, Harrison Sushiro from Yale University, used to be here at SMU. So he designed this code that works by using elliptical isophote analysis, which is a very technical term to explain what's going on in this image. Basically, we fit these ellipses to a galaxy, we sample along its major axis, but the crucial part is that the brightness values that we measure into the 1D profile are averaged around these ellipses, so it increases your signal to noise greatly in the outskirts of galaxies where they're very noisy, and so that's what allows us to get at this outer stellar halo material and reliably measure those brightness levels. So the code also does a number of other things to make sure that we're getting reliable stellar halo measurements, right? We're getting reliable profile measurements in these outskirts. First thing is we're going to mask foreground background sources. So that's what's shown in panel A and B here, blocked a little bit by the thingy. But so the white patches you see in panel B here are just galaxies from this image that are blocked out because we don't want their light to contaminate the profile that we extract. And then the next thing is that there's going to be some residual background noise that varies across an image, something like panel D. And so we have a 2D background subtraction procedure that does this on every image, that basically subtracts off this residual varying background noise. So what this allows us to do is kind of summarized in this profile plot here. If you ran everything as you should get the red profile for this galaxy. But if you don't do this masking and background subtraction, you'd get something like the blue profile. So you would get an unreliable halo brightness measurement and would kind of throw off our interpretations. So it's really important that we do these corrections. And the other correction that we do is for the instrumental effect from telescopes. So specifically their point spread functions. So this is basically the effect where if you looked at just a laser point-like bit of light through a telescope's instrument, it's actually going to be smeared out a little bit like this blob here in the middle. And what this does to a galaxy's image is actually suppress the brightness levels in the inner regions and smears it out to outer regions. It kind of blurs the image. And so what the effect this has on the profile you would extract is shown with this red and black profile here. Depending on the type of galaxy, that's what the two panels are showing, you should get something like the red, but because of this PSF effect, you get something like the black. And so in my master's work, I designed this code that uses simulated data to help correct for this effect in observational data and removes this effect on profile, so corrects for the PSFs.
Do you run that correction before any deconvolution of the image or after?
Yeah, so this essentially the code that runs and does this correction is in essence the deconvolution. Yeah, it's more of a forward modeling approach, and I can get into the specifics after if you're interested, but yeah, this is basically the deconvolution step of getting rid of that PSF effect. I think I lost my clicker. Oh, there we go. Okay, so the last thing about my methodology that I want to cover before we get into the good stuff, into the results, is when all this is said and done, I have all of these corrected images, I've extracted light profiles that have reliable halo measurements for hundreds of thousands of galaxies. I don't just study one galaxy's profile, right? Because I only have that galaxy one snapshot in time. What I do is I group galaxies together in smaller bins of time, or redshift, and then I further bin them by mass, so low mass versus high mass, or their type, star forming versus quiescent, and I compute median profiles. So that's what's shown in this middle image here. The blue profile is a median that you'd get from a bunch of individual galaxy profiles in the background. That's the gray. The dashed lines are just showing kind of a 25-75 confidence interval on that median. And then what I do with these median profiles is look at how they evolve over those different time bins, and I compare that evolution with the predictions from simulations. And so that way I'm able to study trends in galaxy growth over large timescales instead of just looking at individual galaxies, just 330,000 times. So that plot on the right is kind of a look behind the scenes of what's going on in my results, but I'll keep things much less technical here as we go through them. On to my results. Where first I'm going to cover what was in my first paper. It was published in AppJ last year, called The Growth of Galaxy Stellar Halos. And I first want to talk about the halo growth that we measured in the different galaxy subpopulations. So again, to orient yourselves, I looked at low mass, star forming, and quiescent galaxies, high mass, star forming, and quiescent galaxies over a period of about 6 billion years. And what we found was that the high mass galaxies are growing their halos considerably faster than the low mass galaxies. About a 70% larger increase to their halos from the oldest time bin to the youngest time bin. So the exact growth factors are shown on the right here. The one that's cut off, I think, is 2.8 for the small quiescent galaxies. And the other takeaway is that at a fixed mass, so if you just look at the low mass or you just look at the high mass and you compare red versus blue, you find that the red galaxies, the quiescent ones, grew their halos about 20% more over the same time period. So already that's a little puzzling, right? The galaxies that are not forming stars are growing their halos more than the ones that are forming stars. So already this is starting to indicate, okay, maybe this is coming from mergers. The next thing we wanted to look at was where in the halos this growth is occurring. Is it just uniform throughout the entire outskirts of the galaxy, or does it kind of pick one region over the other? And what we found is there is quite a difference between the two types of galaxies, the red and blue ones. So the quiescent galaxies, they grow their inner halo and their outer halo by very similar amounts. About 44% of the total growth happens in the two regions. Within errors, it's pretty even. The star-forming sample was quite the opposite. They grow their inner halos much, much more than their outskirts, about 78% to 22%. And so what we think is driving this is different mass assembly mechanisms that are driving the growth in these galaxies. So to explain that, in quiescent galaxies, we know they're not forming stars, they're likely growing through mergers, and we think the leading prediction is that these are minor mergers. So remember at the start of my talk, I said minor mergers, the smaller companion is just going to kind of get shredded apart, and its material is just going to get distributed amongst the larger galaxy, kind of evenly throughout its outskirts. So that might explain why there's an even amount of growth in the inner and outer halo portions of these quiescent galaxies. Star-forming galaxies, we think much more of their growth is coming from star formation, which is going to happen more in the inner parts of the galaxy than it is the outskirts. And some of these stars can, in theory, migrate outwards into what we would call maybe the inner halo region, kind of just outside the disks. And so that might explain this discrepancy where they're doing a lot more growing in inner regions because it's mostly star formation, but maybe a little bit of merging happening in the outskirts, and that's where that 22% is coming. So we wanted to dig a little bit more into this with our star-forming sample, right? Could the halo growth that we're measuring, in theory, come from star formation and just have these stars get kicked out to larger orbits and kind of look like a bigger halo? And so what we did was we took median star formation rates for our sample, multiplied them over the time range, gives you an estimate, kind of best case scenario, how many stars could you form, and could this explain the growth that we measured? And so that's what these two vials show for our low mass and high mass star-forming galaxies. And what we found was that for the low mass star-forming galaxies, their just little bit of halo growth could be explained by star formation. You could, in theory, form enough stars. Doesn't mean they all do that way. Maybe some of them do some merging, most of them go through star formation, but it is possible that our results are driven by star formation. The high mass star-forming sample, much different story. Star formation, even in a perfect case scenario, can only account for about 44% of the growth that we measured. So that means over half of the growth over the last 6 billion years that are happening in these massive disk galaxies are coming from something else, likely mergers. And so on that note about mergers and their contribution, remember this plot from earlier in my talk, these predictions that we have about how much mergers should contribute to different types of galaxies? Well, we were able to provide many more observational tests of these predictions, not just in one time bin, but 4 time bins. So that's what these 4 panels show. And the big thing is the size of the sample that we've provided for these tests for the simulations. So my black points here contain anywhere from 5,000 to 20,000 galaxies, depending on the bin, whereas these points from earlier that I talked about in the top were like a handful of galaxies. So this is a much, much better constraint on our theoretical models, improves our simulations about how much mergers are really contributing. To give you some numbers, what we found was that in low mass galaxies, mergers over their entire lifetime are going to contribute about 5 to 10% of their total stellar mass. So not negligible, but not a large amount. But in the high mass sample, it's a much, much bigger contribution. Anywhere from 25 to 50% or more of the mass growth that occurs in big galaxies over their lifetimes are going to come from mergers. And more specifically, our results are really hinting that it's minor mergers that are driving the majority of our results, not major mergers. And there's a few line of reasoning that got us there. One is the fact that these high-mass star-forming galaxies are growing through mergers, but they still have their disks. Their disks haven't been destroyed. So I said earlier that major mergers are so chaotic and turbulent, they're going to destroy disks. So that's one indicator that it's likely minor mergers. The other thing was the slopes. So I talked about different slopes in these profiles and how they change over time may indicate whether it's minor or major mergers based on the simulations. And so the slope changes that we were seeing much more aligned with the minor merger scenario. And then lastly, the amount of material that the two types of mergers would donate kind of helped with this interpretation. Because if it was a bunch of major mergers, right, two similar sized galaxies merging together, forming a bigger one, you'd expect much higher percentages coming from mergers. So that all really leads to big galaxies eat small galaxies, minor mergers. The other key takeaway that came out of this work was that at a fixed mass, the quiescent galaxies are growing more through mergers. About 30% larger increase in their accreted mass fractions, the fraction that's coming from mergers. So the takeaway here is that mergers contribute more to big galaxies, and they contribute more to the red quiescent galaxies than the star-forming ones. And so that brings me to the second half of my results, which is more recent work It hasn't been published yet, so I'm going to say, take everything with a grain of salt. But we are in the submission phase, so we've done a lot of vetting. We're pretty confident with these results, so I'm happy to share them with you today. But yeah, just need to say that it will be soon submitted and published to AppJ, so stay tuned for that. And this looks at the cluster environments. So we talked about the cosmic web environment, specifically these dense cluster regions. So what I did was a very similar analysis I did in my first paper. I compared the stellar halo evolution of 2 galaxy samples over time. Specifically this time I looked at a sample of cluster quiescent galaxies and a sample of field quiescent galaxies, or what you can think of as isolated. They don't necessarily live in those cosmic voids that I mentioned earlier. Some of them might, some of them might not, but they definitely are not in any cluster or large group. They're kind of by themselves. And 2 real key results came of this work. One is that cluster environments do have an impact on stellar halo growth, and I'll talk about that in a moment, and the size of the cluster makes a difference. So, in high mass cluster quiescent galaxies, their results were pretty easy to interpret. They have bigger halos at any one point in time, so you compare cluster to field galaxies. The high mass galaxies, they have bigger halos and they grow these halos faster. And we think that that's coming from them being able to have enhanced halo growth through increased mergers. So in these cluster environments, there's more things around for them to merge with. They are able to continue merging in these environments. They're having enhanced growth. Now, the low mass sample had some more puzzling results that were a little difficult to interpret at first, because what we found was that, like the high mass sample, they also are growing the halos faster. So that's comparing a cluster sample to a cluster sample to a cluster sample over different time bins, and then comparing a field sample to a field sample to a field sample. You see that the cluster galaxies are growing faster. But if you compare the 2 samples at any one point in time, you actually see that the cluster galaxies have about 10% smaller halos. So a way to interpret this is, think of my friend has $100 and I have $1. Every hour they gain another $1, but I gain $2. So I'm growing my money faster than them, but I still don't have more money than them, and I won't for quite a few time bins. So that's what's going on here. There's something in the cluster environments that are causing smaller halos around these low mass galaxies, but something between the time that they were isolated galaxies, travel through the cosmic web and enter a cluster, something during that time is causing them to have this slightly enhanced rate of growth, this 21%. So we think what's happening is that these low mass galaxies are able to do a bit of merging, a bit of growing in what we call intermediate density environments. So the filaments of the cosmic web as they funnel things towards clusters, or you could be kind of in this region as you fall towards a cluster, and maybe you start to group up with some galaxies around you as you get closer and closer. So they're able to do a little bit of fast growing during that time. So that's why they have faster growth than the field, but there's something in the clusters that's stripping their material away. And this result was really solidified when we looked at a different result, and that was, does the size of the cluster make a difference, right? Whether you're in a smaller, less populated cluster or a much larger, more populated cluster. And what we found there was that the low mass galaxies, as you went to bigger and bigger clusters, they had smaller and smaller halos, which means that this stripping effect is getting stronger and stronger, which is what you'd expect in bigger and bigger clusters, because that dense, turbulent cloud of gas that we looked at in the video is just going to get bigger and denser and hotter and more turbulent. So it's going to create a stronger effect. So actually there was about a 25% reduction in the stellar halos of galaxies, of cluster galaxies in the biggest clusters compared to the smallest. The high mass sample was the opposite. As you went to bigger and bigger clusters, the high mass cluster galaxies had bigger and bigger halos. So what this told us, really solidified, is that these high mass galaxies in these harsh environments inside these cluster regions, they're not affected. They're resistant to these harmful conditions, this fast turbulent gas. It's because they have a lot more gravity, so they're able to hold on to all of their things. Instead, they just have more and more enhanced growth. They're in bigger clusters, there's more things for them around to merge with, there's more of those smaller galaxies for them to eat up, so they just get bigger and bigger and bigger. And that's how you get some of the largest red elliptical galaxies in the universe, like M49. And so with that, this brings me to the end of my talk. So I'm just going to summarize some of the key results here and the takeaway points, to share with your friends of what you learned about galaxies this weekend. So over the 6 billion years that we studied, we found that high mass galaxies grow their halos faster than low mass galaxies. We found that quiescent galaxies grow their halos more than the star-forming spirals, and they're growing their inner and outer halos very comparably, whereas the star-forming galaxies are growing their inner regions more than their further outskirts. Star formation can explain the growth in small blue spiral galaxies, but the big blue spiral galaxies, they need growth through mergers, as do the quiescent galaxies. And these mergers are likely minor mergers that are contributing more to the growth in big galaxies or the red galaxies over the blue ones. And then lastly, the results of the cluster environments. So we found that the high mass cluster galaxies, they're resistant to these harsh environmental conditions inside clusters. They're able to have enhanced halo growth through increased merger activity. The low mass galaxies are the opposite. In these dense regions, there's the hot turbulent gas is too much for them. It can strip away some of their material. The bigger galaxies start to eat away at them. So they actually have suppressed growth and more of this stripping occurring. And then lastly, the size of the cluster makes a difference. Bigger and bigger clusters, the stripping effect's going to get greater in low mass galaxies until they're finally just kind of eaten apart. And then big galaxies, bigger and bigger clusters just gives them more things to merge with. Their growth is just further enhanced. And that's how you get some of the biggest, reddest galaxies in the universe. And so with that, I'll say thanks very much for listening and happy to take any questions.
Thank you so much. That made it really accessible.
Yeah, so I hope that's what I was going for. Yeah, it was general audience level.
I have a background in sort of like computer vision and modeling, and I was really curious about some of the elements of modeling the data. For example, the models we saw of the galaxies moving around each other and over time, the animation specifically.
Yeah.
Is that just Newtonian, or does it factor in? Does it have to factor in any relativistic effects? Does it factor in other forces, like say electromagnetic? For example, if a star-forming galaxy had more gradient of pressure due to supernovas or some other outgassing, it would actually blow off stuff.
How far back are these?
In a more quiescent galaxy because there's less energy coming out of it?
You repeat the question?
Yeah.
Sure. So
As I find
No, I meant, so the mic can pick it up. Okay. Can we hear?
Yep. Sorry, do you want to repeat the question?
no, for you to say it. So the
Oh, on the mic. Okay, so you're asking whether so these simulations showing how galaxies are existing in cluster environments, whether they take into consideration some of these other physical process or magnetic fields, feedback from galaxies. So there's two answers to that. Depends on the simulation. So there's what we call just cosmological kind of dark matter simulations or N-body ones. So these really just look at how things move under gravity. And so this kind of gives us this picture. There are magneto-hydrodynamical simulations, which have this crazy, complex prescription of all of these different forces. So we take into consideration magnetic field strengths, electron ionization temperatures, all sorts of things like that. But that's where things can get kind of very messy, because you get into the weeds of the physics and how you incorporate those physics in the code. And so that's what led to, early on I showed this plot of the different predictions from simulations and how they all kind of varied. So that's those physical prescriptions in action is basically, they all kind of touch on, so these different color curves is what I'm referring to. So you can see that some of these semi-analytical models, for instance, wouldn't have a lot of the things we just discussed, but stuff like a lustrous TNG, they do have a lot of those magneto-hydrodynamical forces worked in. So it can get very, very complex. The more complex you make it, the kind of harder it is to test. Right, because we don't know a lot of these things about galaxies, their magnetic field strengths or certain properties. So yeah, it's great that these sims might tell you that, but how do you test it? So sometimes it's easier to compare with more simple simulations first.
Thank you.
Yeah. Yeah.
So your first set of analyses shows that more massive galaxies acquire halos at let's say, a faster rate.
Yeah.
Does your image data show, when you're not in a cluster, obviously, those larger galaxies having more small galaxies around them? Or is the distribution similar between the massive galaxies and the small galaxies?
So my work specifically doesn't look at that because as I showed in that image with the masking, I actually mask out the other objects, so we don't actually do a lot of counting. But we do have someone in our group that works on this. Satellite galaxy distribution is what it's called. Basically, how many small galaxies do you find around a bigger galaxy? And this does change with the galaxy's mass. We typically do find that the bigger galaxies have more little galaxies around them. But again, it's one of those things like we can catch glimpses of mergers or maybe soon to be mergers in action, but we don't know for sure that it's going to happen or how much material is going to swap. And so yeah, that's kind of the name of the game is getting at that. But yeah, so they do change in their satellite distribution. Oh, yep. At the back there, so then I'll come back this way.
So can you tell me again how you measured the rate of halo growth? Did you look at individual galaxies over that 400-day period?
Could you repeat that?
Yeah, so the question was, how do I measure the rate of the halo growth? To answer that, let me get to a couple of slides here. So the first thing is, as I said, once we have all these individual profiles extracted, what I do is form median profiles. So I have a whole bunch of median profiles, basically a bunch of different mass and galaxy bins, the star-forming quiescent, over different time bins. And so how I measure the rate of the growth is basically, if you look at this plot here, you can see this shaded purple material gets larger and larger and larger with each profile. So these are different snapshots in time, different median profiles at different points over that whole 6 gigayears. And so you can just kind of quickly do a back of the envelope calculation of, well, if it grew by 20% over a gigayear and then 30% over a gigayear and a half, and kind of add them all together, and it gives you a rough idea of over the full time period how much growth occurred. And that's where we found the massive galaxies grow about 70% faster, about 70% larger increase in this shaded area from the oldest profile to the youngest.
Are you able to track an individual galaxy or just a small cluster?
Yeah, so each galaxy we just have one snapshot in time. So we can't really trace one galaxy, how it changes. There's a bit of things with cluster galaxies that you can, based on if you can get some good radial velocity measurements and some measurements of the velocity dispersion of the cluster, you might be able to tell whether it's on its first infall or whether it's been doing a couple orbits of the cluster or what kind of direction it's coming. Maybe it's traveling down one of those filaments, or maybe it's just coming from a void. So you can start to get at that kind of information, but it needs a little bit different data than what we use. So we need some spectroscopic data. That's what gets you a lot more accurate velocities. So in my work, no, I don't trace one galaxy. It's more how does a population of galaxies change over time by looking at a big sample over here, big sample over here, big sample over here, and so on with time.
Would you be able to track a single galaxy with other spectrographic assessment?
No, because it's still just that factor of the universe that we're, if they're a billion light years away, then we're looking at how they existed a billion light years ago, and just every second is just another second forward. So it's, if you looked at one galaxy, this year and next year and the year after, and maybe for 100 years, you might be able to start to piece together some sort of evolutionary thing with just one galaxy. But obviously, I don't want to take 100 years to do my PhD, and that might not even really get it at what the galaxy is doing over a large time scale. So that's why I really need to get at it with this kind of population sample approach. Yeah.
Are upcoming satellites or telescopes like Nancy Grace Roman going to help with this?
Yes, actually, that's a great question, and it's something I didn't add to my talk, just in the interest of time. But I have a third paper that's in the works. That's going to be the last project of my PhD, and that's going to look at the other environments in the cosmic web. So in this talk, I just focus on the clusters, but those filament regions, those branch-like regions that are connecting them all, I want to get at galaxies in those regions. So with that, we need a little bit better quality data because we need to be a bit more accurate with their distances to really map out the 3D cosmic web structure. And so with that, we're actually going to use the Euclid Space Telescope. So we're going to use some of its data to help pinpoint exactly where the cosmic web features are by using some spectroscopic information. And then we're going to have a much larger photometric galaxy sample that will add to that afterwards. So we're going to kind of use a bit of CFHT data, a bit of HSC data, but then complement it with some new Euclid Space Telescope data. That's really going to help us get at different environments.
Any questions from Zoom land?
Oh, yeah. Oh.
On the topic of smaller galaxies getting absorbed into larger ones, would M51 and NGC 5195, I think it is, be a perfect example of that?
I don't know this off the top of my head, but
Wormhole galaxy.
it very well could be. Does it look like?
I didn't see a picture of it.
Oh, yeah, it might not have. I will say I have a lot of images of mergers in action. But yeah, if it's a bigger and a smaller galaxy, like actually I do have one double spiral example somewhere here a moment ago.
Popular telescopic.
Yeah. Something like that, maybe.
Like that.
Yeah, so that's the minor merger scenario, the big galaxy eating smaller galaxy. Yeah, that's kind of the idea. Yep.
If I can ask one more question, how do you pick a PhD topic and how do you stay with it through all the ups and downs?
That's really two questions. How do I pick the project? Oh yeah, so is asked how do I pick a PhD project and stick with it over the time frame. So how I picked the project was actually pretty much picked for me. It was a project pitched by my two supervisors. So I worked with them during my master's on kind of very similar stuff, a lot of the code that was kind of needed to run this project. And then they pitched me this project of studying merger growth through these stellar halos. And what really drew me was the environment stuff, because it was right around that time that I learned about the cosmic web. I thought that was really cool, that it isn't just random if we look out in space, that there is actually this crazy, large, universe-wide, network of things going on. And we don't really know a lot of else other than the fact that it exists. So that really interests me, and I wanted to study those cosmic environments more. So that's the project. How do I stick with it? A lot of stressful long nights. Yeah, because science is fun sometimes and other times it's not, because things don't always work the way you'd like it to, or code breaks. But if you have a project that you really, really like, the material behind it, and really want to answer those questions for yourself, not just for your job, it makes it all worthwhile and pretty easy to stomach.
So Devin, your third project, that is not time delimited much, but your PhD is, for instance.
Yeah, no, so it is. Part of our PhD program here, they're different kind of wherever you go. We have to have 3 bodies of work, not necessarily published papers, but 3 papers worth of material by the end of the PhD. And I need a little time to actually do my whole dissertation. So I pretty much have to have the third paper done, hopefully by the end of this year, if not before next summer. But fingers crossed that we don't hit any issues, and then we'll make that on time. But I'm feeling pretty confident about it. But yeah, so not always they come out in published works. I've been very fortunate in that sense that already my works, the first work has been published. The second one will be published in a few months, and we're planning on publishing the third as well. So very nice.
Do you have a chance to look through a telescope?
Yes, actually. So as Judy pointed out, mentioned, I work at the Burke-Gaffin Observatory here at SMU. So I do actually get to look through Ralph, our telescope, quite regularly, whether it's on public tours or helping students. But I have been trying to weasel my way into some of the internships or summer co-op programs that they have actually at the telescopes that I use. So CFHT is one of them, for instance. So I've been trying to get my supervisors maybe to push in that direction. They send me there for a summer, but more on that. But yeah, so I have had a little bit of experience with the observational side, thanks to the BGO here. Any more questions? Oh, one more in the back.
The cosmic web.
Yeah, sure.
I imagine you don't really know the answer, but when you think of from the beginning of time to now, and things like the cosmic microwave background is almost uniform, but this clearly does not look uniform. I mean, you think it's mostly for galaxy evolution and mergers must shape that a little bit, but there must be other things too.
Yeah, so how the web forms is, I don't want to necessarily, it's still debated, maybe just poorly understood. It's coming from dark matter, so the outer structure is formed from dark matter, and we think that this structure formed before any stars and galaxies. So very early on after the Big Bang, the dark matter would have started to form this larger kind of network, and then this, through gravity, attracted the baryons that would then form, gas clouds, which then form stars, which then form galaxies. So we think the dark matter structure came first, and things fell into it. But still kind of work to be done on that front. It's very difficult to study that. A lot of it is, simulation or theory based. It's tough to test a lot of that. But it is just really neat. It's one of these things, we don't know a lot about. We don't know a lot about dark matter, but we know that this cosmic web exists because we can place galaxies. We have their coordinates, we have their distances, you map them out, you look at a 3D model of what's been mapped out, and it looks like this cosmic web. And so it's really, really cool that, it's something we can see, but still don't understand. So that's why it really interests me, that cosmic web.
Sounds like someone else's PhD.
Yeah, I won't figure it out in the next year, that's for sure. So hopefully I've inspired someone here to go and figure out the problem. But yeah.
Thanks so much, Devin.
Yes.
That was really exciting to see and to hear. And I'm sure the next time we look out through our actual scopes, that we'll think about this and look at the world of the exterior world a little differently, with a different thought in mind as to how that thing we're seeing in our scope actually came to be. So thank you very much.
Yes, thanks for having me, everybody. There we go.
And number 2. Okay, and I think next up is Tony McGrath and Michelle Lane regarding the scope fund. So I'll leave it to you two.
Well, I'll pass the baton to Michelle. They were just, it's a very exciting day. We spent a year with the Dave Lane Memorial Scope Fund, and we've had a number of contributions to it, and everyone has a great idea about the background of that. And so we closed the Scope Fund fundraising episode in the end of last year, and so which brings us to the point now where Michelle is able to conclude the Scope Fund with the matching contribution. So Michelle?
Thanks very much, Tony. When I stood before you about this time last year, I said it would be my greatest pleasure to be able to provide a second gift. Last year, I provided an initial, inaugural, and starting point of $10,000 to begin this fund. I said I'd love to match it with $5,000 if everyone were so inspired to actually rise to the challenge of donating to match. And you did, beginning with the most incredible starting point of all, which was Tony Schellink, and I'm sorry that he's not here today, but Tony kicked us off with actually his own $5,000, and then everyone else stepped in. So we're still waiting for a final tally, but I think we're somewhere in the 25,000 tally with my contribution today of that promised $5,000 match. And because of the tremendous good work that people like Blair and Jerry, and I think others, have been doing behind the scenes with partners at Atlantic Photo to launch the sale of images, there is even more opportunity to grow this fund, which is tremendous, just tremendous. So everyone, a big round of applause to what you have done and continue to do. It's really outstanding. And so I am really delighted to be able to hand you this check today with my...
Want to take a picture from that side?
We could do that.
Yeah, that's what I'm going for.
Thank you. And if I may just say a few words, with your permission, President. You know, it's interesting what you find when you start going through treasures. And I was going through some things in Dave's office not so very long ago. And I came across this wonderful piece of parchment that I thought was just a wonderful punctuation point to today's conversation about this fund, which we created in his honor. You know, Dave felt that the St. Croix Observatory was the jewel in the crown of this center, a very special place, and he was, with many of you, instrumental in its building. And back then there was a fundraising project with images. I think it was Comet Hale-Bopp that was instrumental in the raising of funds. And I got a real chuckle when I found this parchment because it was a recognition certificate signed by Dave. You may remember this, Dave Chapman. You were the center president at the time. Pat Kelly was observatory fundraising chair, and Sean Mitchell, the observatory chair. Date is February of 1997. And the certificate to Dave was in recognition of the support given to the Halifax Centre of the Royal Astronomical Society of Canada in the building of its observatory at St. Croix. And Dave Lane is awarded this certificate of appreciation, and wait for this now, at the level of Galactic Supporter, which I thought was pretty apt. He would not have been the only galactic supporter, there would have been a whole team. But I thought, isn't that very typical of the extraordinary effort of Dave? And with your help and this fund, that beautiful observatory in St. Croix will now have a property endowment fund and a stream of revenue. So I'm thrilled that this has come to be. I do also want to tell you, and this is a surprise to Tony, that I hope to be back here in a couple of years. It's certainly my intention, if you're willing to have me, because I think funds like this need to continue to be fostered and enriched. And I would like to come back before the 5th anniversary of Dave's passing, and then that's just a few years from now, and talk to you about another little project in support of St. Croix and perhaps a matching opportunity that might so inspire you at that point in time. And so I'm going to make that promise today and hope to be back to talk to you about that. With your indulgence, I also wanted to say just a few words about another legacy project that Dave and I started before his death. And that's one that Tiffany has been very involved in, along with her team, and Andrea Meisner, who is known to many of you, but a team here at St. Mary's. And that is the Starfinder program, which is the Dave Lane Astronomy Outreach Program, which is a remarkable, enduring endowment program to carry on Dave's work in public education and outreach. And one of the central elements of it is intended to be workshops for teachers to provide them with the skills, the knowledge, the tools, because this book, which was created last year by the team, is filled with lesson plans to allow teachers to bring astronomy into the classroom, targeting grade 9, and eventually there will be a complementary program for grade 6, and to work across Nova Scotia. Last year there were 12 teachers from around the province in that first program held here. And I want to single out Ben O'Toole, a new member here, a relatively new member, I think, at the back of the room. You want to stand up, Ben, so everybody can recognize you? Ben was not only a member of that cohort, but Ben is a teacher at Parkview Education. Another lovely link, because it was at Parkview Education that Dave got his first real foundational skills in astronomy. He already had an interest in the stars, but it was at Parkview, under the guidance and inspiration of his teacher, Wilf Morley, that the sparks were ignited. And the rest, many of you know, he went on to do many great things. And it is my hope, and it was certainly his before his passing, that this program, the Starfinder, which Ben is a part of, would in fact generate year by year, because it will be a program living on in perpetuity, the ranks of the next generation of astronomers, perhaps the future members of this center. I'm thrilled that Ben is here today. I hope you all get to know him over time, because he is actively at work. He's already relaunched the Astronomy Club at Parkview. He's been out with them fundraising to build an observatory, to gather equipment. I know there are already some exchanges of equipment happening. I brought some books for him today. Others have been helping him. This is the future for astronomy and for centers like this. And I'm just delighted that he was one of the first participants in that workshop, and a nod to Tiffany and the team for making that possible. It's a nice compliment to the work of the center, and maybe one of these days some of your keen participants at Parkview will get over to St. Croix to have a look there. So Thank you. It's been wonderful to be able to celebrate those things here today.
We'll break now, and I believe Mr. MacDonald has brought some cookies and so have I, so you're welcome to join us for some treats, provided there are any left in the bar, they eat them all. 15 minutes, so that would be, we'll say 2:30.
Okay, we're back on again, and we'll begin with Paul Heath's Food for the Soul.
As most of you know, I try to write a poem based on the topic of the day, so I'm hoping I got close. The long dance. It began. 1,000 million, billion, trillion motes drifting upon the void. The dance began with slow spins and wide skirts outflung, motes swept up till with speckled glowing spun. With dervish spins, the dancers swept across the void. Motes occurred, feeding lanterns brightening glow. They spin in clusters and alone, swiftly outflung across the void, their skirts wide, sweeping motes agelessly through time. A subtle, ever-changing dance. Slight touches of skirts, patterns realigned. Too close, arms entwined to solidary redness are slowed. Large groups draw other dancers close, loose pairings outflung to spin alone. The motes amassed as glistening gems on spinning skirts. For eons the dance will be a dervish spin until the last mote from the void is swept, till the last spin in fading redness slows, until time's last quivered note has stilled. One thing I saw when Judy sent this to me was that there's no period, there's no ending, because we really don't know when time's going to end, so things just fade away. I hope I got close.
Those the cookies to start.
What do you want?
Well, we got outreach opportunities right now. And then,
Presentation?
nope. So just to remind everyone, there's is that the sea star talking to us? There's an outreach opportunity coming up February 23rd. It's a Monday evening at Atlantic Photo Supply. They're hosting their annual Urban Star Party. So beginning at 7. So if anyone wants to bring their scope to the parking lot in front of Atlantic Photo Supply, they have it cordoned off for this event. And I think last year we had, was it 16 telescopes?
Oh, no, 60 people.
60 people, yeah. And at least 10 different telescopes, I think. Yeah. So it was a good turnout. Atlantic Photo Supply provides hot chocolate and Timbits if you need some incentive. If it's cloudy, snowy, or some other inclement weather, that Monday, the alternate date is the Tuesday. So 7 o'clock, Atlantic Photo Supply and their Burnside location. There's one other outreach opportunity coming up if anyone here wants to drive out to Parsboro, or anyone that's online lives in the Parsboro area. The Cliffs of Fundy Geopark, as part of their winter carnival, is hosting a stargazing session on the 15th of February. That's a Sunday evening at Glooscap Park. So if you're up there at around 6:30, I'm sure they'd be happy to see you there.
David, on the Atlantic Photo Supply site, if anyone wants to have a spectacular view of Jupiter,
Yeah.
they have some of the best seeing in HRN, and I do not know why.
Yeah, it's a little challenging for anything other than planets, globular clusters, or open clusters. But we've also got around was it first quarter moon or? Yeah. So. Yeah, exactly. So it's always fun to look at the moon and Jupiter. Okay, so now we have news from the board. Tony, are you going to take that?
Thank you, David. Just before I get to the news from the board, I have a special announcement. Please join me in congratulating our own Judy Black on receiving the Society's Service Award. The Service Award is a major award presented in recognition of outstanding service delivered to the Society over an extended period, and it's hard to imagine a more deserving recipient. Over her 12 years of membership, Judy has consistently demonstrated exceptional leadership, organization, and dedication in all that she does. Our RASC Halifax Centre owes a great deal to her commitment, her generosity of spirit, her steady willingness to step up whenever it is needed, and we're truly fortunate to count her among us. Presentation of the award shall occur at a future public meeting, and details will be announced prior to that meeting. So congratulations, Judy.
Thank you all.
Okay.
Right to the end. You should have got two.
Oh, thank you. Oh, man.
Picture under the end.
Under the
Okay.
this thing?
Yeah.
This thing?
Smile.
I'm trying to.
What a surprise.
Two.
Oh. It was, yes. So this was the something you said you had to say?
Yes, this was it. And now I've said it. So continuing with the news from the board, just a couple of reminders that our mission for this year is we're trying to encourage folks to become more involved in the centre. So small specific roles, one-time opportunities. There'll be a couple of those come up. We've got a little bit of work to do with St. Croix. When the weather moderates, we'll get a plan together to do that. So there'll be some opportunities to volunteer there. December is approaching and a new year, and so think anybody who's interested in what the board does or the committees of the centre, great time just to tag up with some people over the next number of months, if you like, and just learn a little bit about what it takes to plan Nova East, or what it takes to do some outreach, or what it might take to do anything, or what goes on the board. We'd very much love to have you participate. And finally, member-led projects. Again, if you have something you're interested in, bring it up. If we can find a way to make it happen, we will do that. Things like a specific observing night or a workshop or an outreach that you are interested in, or even a presentation on a topic that you're interested in that you think others in the centre might be interested in. It doesn't, anything of that nature. So just want to encourage folks to think about that kind of stuff. Don't be shy, and please step forward. As today we had the formal presentation, of course, of the final check from the Scope Fund. So we're really thrilled about that. And as Michelle pointed out, it is the jewel of the center. We're really fortunate to have it. Looking forward to getting back there. It's, you know, with all this snow and cold weather, we don't really get a chance to get to St. Croix, but hang in there, spring is coming. Now, Blair is here. I'd like Blair to have a quick chat about the Astro Image contest, the sale of Astro Images. And again, the funds from that will find their way to the Scope Fund for St. Croix.
Yes. So the slide pretty much says it all. For those that are interested, Jerry, I don't suppose we have any information from the website that you can access from here. Just to bring the pictures up. Or that might be pushing it.
I think that might be pushing.
Okay. At any rate, there are 6, if I remember correct, Jerry, astrophotos from several members, and they are for sale on the site. If you go to the center's main page, under the news column, there's a link there to the site where you can actually purchase the images. You can purchase any one of them, and they're printed at Atlantic Photo Supply. You can either pick them up or have them delivered. There is a delivery charge, so you can just pick them up there if you're in town. And all the funds from the sale of the images go to the Scope Fund. So please buy now and buy often.
Thank you, sir. I'll see if my knees will keep me upright. Stand over here, so hopefully. Okay. All right, that's still the Scope Fund. All right, so.
Down.
There we go. Okay, Nova Notes. This is our newsletter, Senator newsletter that goes out 5 times a year, thanks to the great work of Lisa Ann Fanning and John McPhee. This is the last edition. There was the November-December issue. The cover on it is Jason Dane's photo of the Northern Lights taken at Astrophoto. Every issue is always jam-packed full of stuff. Articles written, for instance, our outreach chair does an article on moonscapes. Mary Tranquillitatis was the last feature that he wrote about, but there have been others. Last month's issue had our 2 poets. Not only was Paul in it, but also Mary Lou Whitehorn. Message from the President, and all sorts of other things that we'd be interested in reading about. One thing to note, that anyone can contribute to this. If they have an observing session that they're really keen that, guess what happened at this session? We'd love to hear about it. All you have to do is write your article and submit it to our editors at novanotes@halifax.rasc.ca. To be included in the January-February edition, just think of Valentine's Day. It's February 15 that Lisa Ann would like your submissions to her. So please consider that. Down. Dark Sky Weekend is coming up, so don't forget to mark your calendars. And if you forget from this presentation, please note that it is also in your Observer's Handbook and on the calendar, the Observer calendar. So the dates are both there, and they're on our website too, for that matter. The Dark Sky Weekend is in partnership with Kejimkujik National Park, and although the details of the actual event have not been worked out yet, we do want to bring to your attention that Peter Hurley, who's one of the, co-hosts or co-organizers of this with the park, did send out an email to the membership at large about it. If you want to volunteer, please contact him or Tony Schelling regarding volunteering for this. There are some sites that have been designated for volunteers, but you have to be willing to partner up on sites because they, like I said, we are limited. If you plan on bringing a family, or if you have an RV or a trailer, you do have to book your own site, unfortunately, okay? So please note that the park opens its bookings at 8 a.m. on February 11, and you better be ready at a.m. because they might be all booked by 8:15 or 9. You know, they go quickly, so just make a note of that. Second up is our Novi Star Party coming up the following weekend. Keep in mind the new moon is between these two events, although the new moon is closer to our Novi Star Party than it is to the dark sky. We are at Smiley's Provincial Park again this year. Our planning team is going to be meeting sometime later this month, so although we don't have particulars again on program and whatnot, we will certainly keep you apprised as things develop. And if you'd like to volunteer at it or participate in the planning team, please let us know. We'd more than love to have you come aboard. Just let me know, and we'll get you lined up to do whichever part of the puzzle you'd like to fill. I'll just reiterate what David said a few moments ago. The public outreach at Atlantic Photo is the 23rd with the cloud date on the 24th. It's at 7 p.m. But if you're volunteering to set up, you might want to be there around 6:30 just to set up and be ready for the 7 a.m. start. And as he suggested, APS is always very generous with their hot chocolate and treats. So, and they have a warm business to go into if you get cold. So it's you're welcome to join us. And again, contact David if you're willing to assist with that. Coming up, we've been making note of this for a while now. There's a observing program called Stellarium, and it's one that you can set up on your computer to set up your observing sessions and all sorts of things. We are having a level 1, which is the introduction to Stellarium, on March 10. It's a Zoom session, and it starts at 7 p.m. Atlantic Hour time, and you'll note that I've cited the Newfoundland time because this is an Atlantic region setup. We've asked St. John's and New Brunswick Centre to join us, so we'll have membership from the Atlantic region, hopefully all three centres assisting in this. And you do have to pre-register for it. The information about registration is on our website. And one of the things that was asked of me at the board on Tuesday night, I guess, was, well, what is the syllabus? And of course, at that point, I couldn't answer. Well, there's the syllabus, and I don't expect you to read this line by line for now. It will be out in an email, but basically it really is the introduction. In other words, what are the components of the program and how do you go about using them? It is for Windows, Macintosh, and Linux computers, but it's not for the paid Stellarium app or smartphones, or the Stellarium web app. So if you don't have those two things and you have the others, you can certainly join us. You do have to have the program preloaded on your computer, and the instructor, Alan McHugh from Calgary Centre, has suggested that you have two. You have one where the webinar is, or the, not the webinar, but the Zoom session is on one, and you're physically able to use the program on another. Because it is hands-on. It isn't just watch and learn. It's hands-on, so you can ask questions actively during the session. I guess I don't have to tell you about this. These are the national awards that the RASC offers. Each has different criteria. Again, thank you so much, everyone, for receiving the service award, but there are others. For instance, the fellow, I think we have the most fellows of any center. I think we have 15 out of the 40-something or other that are out there across the country. Simon Newcomb Award, the Keelak Chant, and the Ken Chilton Award all have their various criteria for different audiences. So I certainly encourage you to look at what the criteria are and think about the membership within the club and who might be deserving of one of these awards. And there's only 327 days left to apply. So you have until the end of the year. We have some observing program certificates and the astroimaging certificates as well. I've circled the Explore the Universe. The main reason being this is the only program that members and non-members alike can complete and receive a certificate and pin. So that, for instance, the kids down your way in your school can all complete this and get a certificate and pin as having completed it. It's a great program for folks that are new to astronomy. It gives you a really good orientation to all the different components that we see up there, everything from the moon to the stars to the planets. And then you can get into, then the members, you have to be a member to receive the certificate for those other programs. That is not to say that a non-member can't download it and complete it themselves. They just can't get the certificate for it. Okay, so just so you know that. Explore the moon. There are two versions, telescope and binocular, so that, and that's where I started, was the telescope version of the moon, then went to binocular, and now I'm doing Isabel Williamson. But it's fun. You get to see so much cool stuff, so getting involved with whatever interests you there. The astroimaging, there are 3 different certificates you can apply for there. The wide field, deep sky, and the solar system, each requiring different numbers of films and types, or pictures, and different types of objects within those fields of topics. And again, I keep trying to encourage astroimagers from our center to, I know you've taken pictures a lot that would fill most of the criteria that these certificates require. So please consider applying. Yes, I know people may not want the recognition, but I think it's still an accomplishment. So please do consider it.
There's also the Astrophoto competition.
That's us. Right. Thank you, Blair, for mentioning that. For those that couldn't hear that, we have an annual photo contest at the center that we announce winners at our annual general meeting in December. RASC Halifax Center members and any resident of Nova Scotia can apply. You can go to our website and you'll find under observing, you can find the astroimaging certificate or astroimaging contest information there. I believe the deadline for submission is November 11 or 12. It's around that time, 10 maybe. It's mid-November anyway, but the date is there on the website. And again, anyone can apply with photos from any one of those 3 categories, because we do give prizes for each of those 3 categories, plus people's choice. In other words, our members are shown all the photos and they get to choose the one that they go, oh wow, that's the best. And they Atlantic Photo Supply, God love them, provide the prizes for them, and it's a print of the winning photo. Thanks for reminding me, Blair. Yes. Explore the universe. There are 110 items, but you only have to do 55, okay, to get the certificate. And with the Explore the Moon, if you do the telescope, you have to do all 94, but if you do binocular, it's only 40 out of the 94. You get to choose which 40. Okay, just so you know. Governance. The board of directors. We're a motley crew of 10 folk. Most of us are here today, so for the people in the room anyway, and I had to write names down so I didn't forget anybody. Tony McGrath, you've met. He's been speaking here. Peter Hurley, who's our vice president. I'm secretary for the board. Dave McMullen is a director. Sorry, David, that's the Dave Hoskin, who's our outreach chair as well as the director. Matt Dyer and Frank Logan. I know you're here, there you are. One of our newest members. We meet once a month, except for the summer months, as you can appreciate. And our next meeting is March 3rd. So if you have anything that you feel that the center should be addressing, please contact Tony. Gone. Oh, there he is, back there. Sorry, Tony. At president@halifax.rasc.ca, and we'll be sure to put it on the agenda for discussion. The other piece of the puzzle for governance is National Council. I happen to be chair of that organization. It's the only committee of the National RASC that is in the bylaw. In other words, that the board cannot unilaterally decide to disband the NC without agreement by the total membership. That differs from all the other committees that the board oversees. There are the members of the National Council are representatives from each of the 30 centers across the country. For every 200 membership, you get one representative for your centers. Centers small like ours have one, and it's me this time. And larger ones can have up to 4. Like Toronto, I think, can have up to 4, but they only choose to send 2. We are an advisory body to the board. Basically, the centers bring things forward to the board for their consideration. The board brings things to the National Council for our input. And that's everything from programming to budget, decisions whether or not to raise our fees, which they didn't do this year, and we had nothing to do with that, just agreed they wouldn't do that. But other considerations. So it's a two-way street here between the council and the board, and it's working very effectively at this point. And we determined there were 3 pillars that we had to work on: communication, collaboration, and transparency. And that's what we've been working towards, excuse me, since 2023, when there were some challenges nationally. Right. Mark your calendars. May 2nd and 3rd is the National General Assembly. It was announced in the recent bulletin from the RASC. It is a virtual conference again this year, and its focus is exploring the night sky together coast to coast. Okay, so that's a Saturday, Sunday, May 2nd and 3rd. Don't have any details at this point, but I'm hoping we will have more come February 22nd when the National Council meets next and the board does report to us what's going on there. Our next meeting is March 7. Blair is going to be addressing summertime photography, and I believe that has to do with, what's what I'm looking for, processing? No? Okay, I'm wrong. I'll let him describe it in March 7. April 11 is members' presentations. We are offering our membership an opportunity to present something of great interest to themselves. And of course the question is, well, the board said, well, what suggestions can we give folk? So I went through old Nova Notes and looked at what member presentations were throughout the eons that we've been in existence. And these were some of the, and I have to go over here because I can't see that. So things like solar observing, flares, sunspots, safety while solar observing, conjunctions, your favorite image. Why is this your favorite image? What equipment did you use? What processing did you use? Why did you even choose it? One of the RASC observing certificates, if you want to describe it or describe how you achieved it. Observing session report, maybe you did an outreach event in your neighborhood for some friends, some family, and you thought this was really cool. I think others should know about this. Keep in mind that whatever we tell our fellow RASC members, it inspires them too. Right? It gives them ideas as to how they can do more than just look through the eyepiece of their telescope or binoculars. Maybe you've traveled. Have you been to an observatory outside of Nova Scotia? Visited another RASC center or astronomy club? Another star party? Maybe you witnessed a space launch. Wouldn't that be cool? And attended special lecture here or further afield. And what about equipment? Do you have a piece of equipment that you have a challenge with? Maybe you fixed it, maybe you didn't. Maybe you're going to come and say, here's my equipment, here's my challenge, help. So that could be a piece too. Review of telescope eyepieces, mounts, whatever. Is it a good mount? Is it a bad one? And why, from your opinion? How to on a special piece of equipment or image processing, etc. What about method of observing? Maybe you're a radio observer or infrared or binocular, or maybe a larger, small telescope, and you want to explain your experiences there and what you found out. And reading, writing, and arithmetic. Book review. Thanks to Tony having a book review one time on black holes, I borrowed his book and I'm now reading it. So it does come as members are inspired. Magazine articles that make you want to go out and find it. I believe, Dave, one year you and I out in the backwoods of Keji took Alan Dyer's 10 items to find in the sky, and we found them.
I found another article in, I think it was Sky and Telescope about the 16 pairs of doubles around Draco. Well, I found 10 of them so far. I'm trying to do it in one session. So it's something that you take and you go out and try and find. And there's another one that I've shared with other members here on the little bull. Pontiac Toby or something like that. It used to be an old constellation, but it's now defunct. And you can find it in the shoulder of Ophiuchus. What about a book review of those kids or children, adults books? One of the book reviews that we had was John Reed's 50 Things to See with a Telescope, for instance. Or maybe you want to review a chapter from the Observer's Handbook. We've done that in the past. And what about an astro image sequence? Maybe you've taken a sequence of sunsets over a period of time, or moonsets, or sunrise, whatever, aurora occultations, or whatever. And of course, if any of you are doing any sort of personal research, or things you're interested in finding out, well, if I do this over a series of evenings, what am I finding out? Come and report it. It doesn't have to be long. It could be 2 minutes. It could be 15 minutes. We leave that up to you. But we'd like to hear from you, and like to hear from other members as well. You can do it here in the room, or you can do it by Zoom. We'll take it either way. So it is, you don't have to do it in person. Okay? It's just something to think about. May 9th is changed, our May 2nd meeting is changed to May 9th, as you can appreciate, because the GA is the 2nd and 3rd. We moved it a week. And although it says the speaker is TBD, we actually, as of this morning, had confirmation that Chris Gaynor from Victoria Centre is going to address, Arrows to the Moon, how engineers from Avro Canada help put astronauts on the moon. So a very Canadian topic. June 6th, we've tentatively slated it to focus around Starfinder. Michelle mentioned it briefly, and excuse me. So we're hoping to have some teachers, maybe some students, look at what the program is, what it's offered, and what have been the outcomes of some of these teachers that have been using the Starfinder program. We have openings for September 12, October 3, and December 5 at our AGM. So if you know of someone that would be willing to speak, or you would like to speak, please contact us. Otherwise, November 7th, Blair has agreed to do Finding Exoplanets. And so that's the end of it. Don't forget to mark your calendars for March 7. Okay? And don't forget to look up. The skies are open, we hope.
Okay, so hoping that the skies are open. This is what we're going to have to look forward to this month in February. The sun this month. Days are getting longer, if not warmer. You'll notice that sunrise is getting a little bit earlier. So 5:52 at the start of the month, 5:16 by the end of the month, the sunset by the end of the month at 6 p.m. So it still leaves lots of time for observing and imaging. This is what the sun looked like today, and I'll just draw your attention to this particular sunspot group. It's quite large. You could, if you go kind of widthwise, you could fit 15 Earths in that particular sunspot. It's been quite active, releasing so far 6 X-class solar flares, but none of them has resulted in a coronal mass ejection that's done more than sideswipe the Earth. So we haven't had any great northern lights out of this particular sunspot. I think there was a G1, maybe a G2 geomagnetic storm a day or two ago. It was cloudy anyway, so we wouldn't have been able to appreciate it. But still, it's still more or less Earth facing, so keep your fingers crossed. We might see something more out of it. The moon this month. So we had full moon at the start of the month. It was cloudy, so we didn't get to see the moon near the double star Regulus. And the 7th, which is today, looks like it'll be cloudy again, so we're not going to see the moon near Spica. February 11th, moon near Antares and M4. 18th, it'll be near Mercury. 19th near Saturn and Neptune. 23rd near the Pleiades. So if we get some good weather towards the end of the month, lots to see. Then we have that's the new moon, the snow blinding moon, on the 17th, and first quarter on the 24th. The end of the month, the moon will be near Jupiter and then near the Beehive cluster. So looking at these in a little more detail, those that had clear skies on the 2nd and were looking through binoculars, that's what you would have seen. So near full moon, close to full moon, and Regulus, double star. I think I've seen some pictures posted on the RASC national website from folks out west that had clear skies and took some pictures. Might have been, I don't know who it was. Alan Dyer maybe had a picture of it. Tonight, if we're, or actually kind of after midnight, there's the moon in Spica. We're lucky. February 11th, moon near, this is a nice one because the moon's going to be a crescent right here, so not a lot of extra light, and bright red star Antares and the Crab globular cluster. That will all be in a field of view of 7x50 binoculars. So that's worth getting up at 5 in the morning, I think, to have a look at if it's clear. On the 18th, we have a very thin new crescent moon here, close to Mercury at 6:30 in the evening. So you need a good western horizon, but you don't need to stay up late. You can just walk out before dinner and have a look. Saturn and Neptune will be near the moon. Again, a nice thin crescent on the 19th. So if you haven't seen Neptune, this is an easy time to see it with binoculars. Saturn's quite easy to find. Nice thin crescent moon, and in between, look just at 1 o'clock off Saturn, and you'll find Neptune. On the 23rd, we have quarter moon and the Pleiades, always nice in binoculars. The 26th, moon, which is going to be pretty bright, but Jupiter's also pretty bright, so you should be able to easily pick those out in 7x50 binoculars. And then the end of the month, we have a nearly full moon and the Beehive cluster, fitting nicely in the field of view of 15x70 binoculars. For those doing the lunar part of Explore the Universe, the time around the first quarter moon is a good time to see lots of the mandated features in that program. So around February 22nd to 26th, it's a good time to get your telescopes or binoculars out and have a look at the moon, see if you can find major craters and mare. Planets in February. So Mars is still too close to the sun to be visible. Venus, starting mid-February, will be visible very low in the west after sunset. Mercury is also very low in the west, beginning at the starting of this month, with, as I mentioned, a conjunction with the waxing crescent moon on the 18th. Mercury will be best viewed February 14th to 22nd, when it'll be at its highest above the western horizon. Jupiter is well placed for observing and imaging, already being high in the east in Gemini after sunset and near the waxing gibbous moon on the 26th. Saturn is starting to sink pretty low in the southwest. So by the end of February, you won't be able to see Saturn. It'll be lost in the twilight glare. But it will be near Neptune all month. So if you want to see that particular pairing, this is a good time. Uranus is visible in Taurus after sunset, setting soon after midnight. And Neptune is visible in western Pisces after sunset, but it sinks lower in the west every day, and it as I said, will be near Saturn. So this is what, if you happen to be looking at Saturn after sunset, next clear night, you'll notice this bright blue star just above Saturn, and that is Neptune. If you have a telescope with sufficient focal length, you'll be able to resolve Neptune as a very small disk. On the 18th, it's well worth stepping out after sunset, because you'll be able to see a nice lineup of planets with a very thin crescent moon, beginning with Venus, lowest on the closest to the horizon, and then the Moon, Mercury just above the Moon, and then Saturn some distance above and to the left. So that might make a nice wide field photo opportunity for someone who has a DSLR or even a smartphone camera should capture these nicely. Okay, this is your chance. If you haven't ever seen or imaged Mercury, this is a good month for it, weather permitting, on the 19th. You may know that Mercury, like Venus and the Moon, has phases, and this is where we're at the, right here, we're at the point of this month of the greatest eastern elongation, around February 19th. And if you have a celestron CH Schmidt-Cassegrain with a focal length of about 2,000 millimeters, or if you have a 4-inch refractor with a Barlow, 200 Barlow, that'll get you about 2,000 millimeters of focal length. With a 5 millimeter eyepiece, this is what Stellarium says you will be able to see. You'll be able to see a part of Mercury, okay? The phase of Mercury. It's somewhere between waxing gibbous and waning crescent. Some years ago, I was able to take a picture using in my case, a 4-inch refractor with a 2x Barlow. This is what you would see in using a standard planetary camera, an ASI 224, with that Schmidt-Cassegrain with a 2x Barlow. Again, you'll see the phase of Mercury, and this is the picture I took a few years ago, actually 6 years ago now, with a 4-inch refractor, 2x Barlow, and that same camera. And you can clearly make out the phase here. I think it was a waxing gibbous. Notice the color, and that's because what's going to be challenging here is Mercury is still fairly low in the sky, so you get a lot of atmospheric dispersion. So the light gets refracted, and you get color in your image from blue at the top down to red. Okay, so don't be surprised. You need a lot of, if you're imaging, you need a lot of frames because Mercury jumps around like crazy, and even if the scene's really good, it's a challenge to get. But anyway, this month is a good time to see or image Mercury. Okay, this month is also when you can start to see zodiacal light. So around the first part of this month, when there's no moon in the sky, soon after sunset, if you look to the west, you'll be able to see kind of a pyramid of light coming up from the western horizon, and that's the sunlight from the sun below the horizon reflecting off dust in the ecliptic. You need a dark observing site with no moonlight, but it's pretty neat to see. Explore the universe. Okay, so winter constellations: Arga, Gemini, Taurus, Orion, Canis Major, and Canis Minor. This is how you can find them. Looking southeast to south just after sunset, and you don't have to stay late to pick out those constellations. The winter stars, major stars in those constellations. It's really easy to pick out Sirius, a very bright star in the sky, and Capella and Rigel are also very prominent, as is Procyon and Betelgeuse. So it's good to learn stars, especially if you have one of the go-to telescopes, because for star alignment, you need to know the star that you want to align your telescope on. Winter deep sky objects. We have two for this month. We have the Pleiades, which you can find here within Taurus, and Messier 35, and that's shown here, and the in Gemini. And the challenge here is that if you can see Messier 35, see if you can also see visually this smaller open cluster, much more distant, NGC 2158. The double star for February is 17 Combe in Coma Berenices. It's a multiple star system. So find the Coma star cluster, and within that Coma star cluster, Stellarium will show you how to find it. So good reason to attend the Stellarium instructional session. But you're looking for a blue and a blue-white star, which is shown here. I don't have a slide for it, but another challenge for you, there is a new supernova visible at the, it's in the halo of a galaxy, NGC 4168. I've seen people be able to resolve it with smart telescopes, with C-Star S30, S50, and Dwarf 2 and Dwarf 3, Dwarf Mini. So if you have one of those smart telescopes, see if you can find it. So all you need to do is punch in NGC 4168, the scope will slew to it, and in the halo, very close to the center of the galaxy, you'll see a magnitude 13 type 1 supernova, type 1a supernova. So it's kind of a neat challenge to try to find. I was able to get a picture of it with my 80 millimeter short tube refractor, and I think a couple hours worth of integration time to get it. So well worth it. Always fun to see supernova. Okay, and that's a fairly new one. It was discovered by Atlas on January 14th. So that's it for what's up in the night sky. If there's any questions, happy to answer them. Otherwise, look forward to seeing everyone here on the 7th of March. Have a good one.
Please hang up and try again.